Good evening, everyone.
Good evening, Ross.
Welcome to the third of three sessions on dimensional modelling, specifically Ralph Kimball's dimensional modelling. Quick show of hands, who came along to one and/or two? Yeah. Okay. Well, congratulations. So you are the few that have passed the test and have been allowed into the final stage. So this is the final presentation I have on dimensional modelling. I have another one yet to come on ETL, metadata in particular, and maybe a couple more in the future if you're interested in that sort of thing. But dimensional modelling, this is it. I have no more to show you after this presentation. Righto, advanced dimensional modelling. So in the very first session, I talked about really what is dimensional modelling, what is a data warehouse, and then in the second one, I went on to talk about the core skills of dimensional modelling, the things that you will use every single day in your career as a data modeller, as a dimensional data modeller. The advanced dimensional modelling presentation, we're going to talk about skills that you won't use every day, but they are still important things. It's important to get them right. If I can draw a little bit of an analogy, if you think about the core everyday skills for a successful marriage, hands up those in a permanent relationship with a significant other. Yeah, okay, so you'll know what I'm talking about. Things like empathy, generosity, communication, shared goals, kindness, thoughtfulness, even fidelity these days. We consider core skills. Now, if you think about those things, or if I think about some of those things, I'll pull out some specific examples. Every morning before I go to work, I kiss my wife and my kids. Also, in the bathroom, I make sure I leave the toilet seat down. Okay, these are examples of my thoughtfulness towards my wife. Not major ones. I don't want to share the intimate details of my life with you, but these are a couple of things that I do as a thoughtful partner. Thank you, Murray. But if I forgot to kiss my wife one morning, or there was I forgot to leave the toilet seat down one afternoon, I might get away with that. In fact, I might get away with it if I did it more than once. I might be forgiven. I might still be judged as a good and thoughtful husband if I failed on these core skills, say, how often do you reckon? Once a year? I'd get away with once a year, yeah? Once a month? Do you think I'd get away with it once a month? Yes. I know you don't know my wife, but Murray's met my wife. I reckon I could probably get away with it once a month. What about something that's not so... what about a skill that's not so frequently demonstrated? How often do you think I'd get away with forgetting our wedding anniversary? Or forgetting her birthday? Do you think I'd get away with it once a year? Right. Once a decade, right. So these skills that you don't demonstrate that often, they're much more important to get right. And they're much more important to get right every time as well. Because the consequences of not getting them right are far greater than those everyday skills. So in work, as in life, we're often held to a higher standard on the little things. So the little things of advanced dimensional modelling that we're going to talk about tonight, here's a list. Hybrid, slowly changing dimensions. Everyone remember slowly changing dimensions from the last presentation? Yes, nods, sighs even. Mini dimensions, junk dimensions, bridge tables, ragged hierarchies, and coverage facts or factless facts. Who's heard of some or any of these things? Who's heard of all of them? Who knows what all of them are? Yeah, what are you doing here? Okay, so this is by no means an exhaustive list of advanced dimensional modelling techniques, but they are things that I've come up against in my career as a dimensional modeller. So therefore I judge them as things that you might be likely to come up against perhaps. There are certainly other things in Ralph Kimball's books that I haven't encountered before. That's not to say they don't matter. It's just that I don't consider myself much of an authority on them, and it's difficult for me to describe a technique that I've never implemented. That reminds me, I do have two of Ralph Kimball's books there. They're sitting beside Murray. Murray will hand them around, and I can hold them up for the camera. There we go. We've got the Data Warehouse ETL toolkit and the Data Warehouse toolkit, now in its third edition, released last year. Thank you, Murray. Hand those around, have a browse through them during the session, and hand them back to the front row when you're done, please. All right. Now, first thing we're going to talk about was slowly changing dimensions. This is something that happens at the beginning of every project when we talk about our slowly changing dimensions. Are we going to make a particular dimension type 1 or type 2? Who's encountered that problem right up front at the beginning of a project before? Yeah? And I've also heard say it's not a data warehouse unless you're using type 2 slowly changing dimensions. Anyone heard that one? Yeah. So it's just me. So the conventional wisdom is that you should be using type 2 slowly changed dimensions, but also the conventional wisdom says that a table is either type 1 or type 2. And so I'm about to discuss what I think that the delineation is not quite so clear. There is no right answer to, is this table type 1 or type 2? Right, so let's have a look at an example. Right, so we've got a customer here by the name of Kim Ralph. She's been a customer of our organisation from the 12th of April 2012, and on that date, the 12th of April, Kim lived in the Northern District, or Northern as defined by our imaginary corporation here. We have this as a type 2 slowly changed dimension. So when Kim moves from the Northern District to the Eastern District, we add a new row to the slowly changed dimension. The day that we receive notification that Kim's moved is the 31st of May 2013. So we insert a new row with from date of 31st of May. We end date the old row to be 31st of May, and the new row we mark with District East, and the old row still has District North. All right, so what about, so this is a type 2 slowly changed dimension here. What about when Kim's name changes? Kim got married to Mr. Ball, and she elected to take on Mr. Ball's surname, so she is now known as Kim Ball. That happened on the 22nd of June 2013, so we insert another new row in the table, same customer number, same old Kim, okay, but we've got a new row. We end date the old row to the 22nd of June. Kim still lives in the Eastern District with her new husband, and so now we've got three separate rows, North, East and East, and Kim Ralph, Kim Ball. All right, so how might we use this? So the top diagram there, that's just a repeat of that type 2 slowly changing dimension that I showed you in the previous slide. Down on the bottom left, I've got a very abbreviated fact table. Kim's had 3 purchases from our company. Okay, those 3 purchases occurred on 25 January 2013, 14 June 2013 and 3rd of September 2013. Coincidentally, each of those purchases coincides with one of those different dimensional time ranges. Okay, so once when she lived in the Northern District, once when she was single and lived in the Eastern District, and once after she changed her name in the Eastern District. All right, so what would happen if we wanted to report sales by district, and these were our 3 sales? So those 3 would roll up between so if we look at the customer key 101, 102 and 103, that matches nicely back to the type 2 slowly changed dimension, 101, 102 and 103. All right, so 101, the $300 transaction, we designate that as North, and 102 and 103, they join to dimensional rows that say it's East, right? So we've got Northern District, our 2013 sales were $300, Eastern District, 2013 sales were $1,400. Perfect. This is exactly why we do type 2 slowly changing dimensions, so that we can get that history. When Kim moved from north to east, we still want those old sales, that first sale, to report under the Northern District. Okay, so this is absolutely normal and as we want it to be. What about this one? So top diagram is the same type 2 slowly changing dimension. The bottom left diagram is the same fact table, but this time we want to write a different report. We want a list of our top 5 customers for 2013. Okay. Now this time our first 2 facts, the $300 fact and the $1,000 fact, have rolled up to a name of Kim Ralph. The third fact, the $400 one, has rolled up to the name of Kimball. So this tells us that we've got 2 customers. Okay, one of them transacted $1,300 worth of business and one of them transacted $400 worth of business. Does this make sense? No. So what have we done wrong?
Customer number.
Could have grouped by customer number, right? So customer number, we could have run our report and said, you know, that SR239994-G transacted $1,700 worth of business, but who is SR239994-G?
Current name.
Got to get the latest version. All right. So sounds like we need to join to the historical row to get well, because that's all. We've got a customer key on the on our fact table. So 101 joins us to our historical dimension row of Kim Ralph, and then we need to join again to the current row to get the name. So it sounds to me like if we're doing that, we're failing on one of the core reasons why we build a dimensional model in the first place, and that is simplicity. So simplicity and performance. Everything we do in dimensional modelling comes back to one of those 2 things: simplicity and performance. So having to join to a dimension, then join to the dimension again on a natural key, filtering on to date equals 31/12/9999, you're raising the bar. You're making it harder for people to get at the information. Right. So I put it to you that just about any type 2 slightly changing dimension is actually a combination dimension. It's a type 2 and type 1 slightly changing dimension. We make these designations not at the table level, but at the column level. Right. So have a look at the diagram at the top. We've got it's still a type 2 slightly changed dimension. Kim moved from north to east, but when her name changed to Kimball, we didn't go inserting another row into the table because the only column that changed was a column that we've designated as type 1. Right, so rather than inserting a new row, what we do is the same thing we do with the type 1 slightly changed dimension. We update the existing row. But instead of updating one existing row, we update all historical rows. Right? So now, when we join this dimension to our fact, we have type 2 behaviour on the district and type 1 behaviour on the customer name. But watch out when 2 things change. If Kim were to get married or change her name and move at the same time, we'd actually be faced with a much more complex ETL situation. So take this example here. If her previous name was Kim Ralph, new name is Kimball, previous district was east, new district is west, what we would do is, those 3 dot points, we insert a new row when the type 2 column changes, that's the district, column changes from east to west. We update the previous row, update the to date of the previous row, so we end date the previous row, and then we update every row when we see that the type 1 column changes. Right, now in the in the 2013 third edition of Ralph's book, he's coined a new term for this, called it Type 6 slowly changed dimensions. You thought there were only 3. How mistaken were you? And you might notice, if you're really sharp, that I've skipped Type 4 and 5. We will get there. He's also come up with a Type 0 that I'm not covering tonight. But I'll leave that one as an exercise for you to look up. Righto, monster dimensions. Who's heard of monster dimensions? Who can imagine what they are? Right, okay, a few imaginative people. Right, excellent. So, a monster dimension is any dimension that's really, really big, okay? Millions of rows, dimensions with millions of rows. We often see them in large retail organisations, less so in Australia, maybe government organisations, you'd see them in Australia. Normally you would find it in the customer dimension or in the product dimension. What we find with these monster dimensions, if we're a large organisation that has millions of customers, like think Walmart or an organisation like that, how interested do you think we'd be in that bottom level of customer, looking at the behaviour of an individual customer? Very interested? Not interested at all? Not really interested at all. What we find with monster dimensions is that unlike our normal smaller dimensions, which we are interested in at atomic level, we have lots of descriptive attributes on monster dimensions. We'll often find that we've got these millions of customers or millions of products, and then we'll find there's 100 or more, hundreds possibly, of descriptive attributes on them. So not only are these dimensions really long, they're really wide as well. They're quite huge. Okay, so think about a monster dimension in the context of a slowly changing dimension. Say we've got 5 million customers. Say those customers have 100 attributes. Then consider what would happen if just 10% of those 100 attributes, so 10 attributes per customer, changed just once a year. So one customer changes 10 times a year. We've got 5 million customers, so that's 50 million changes. Okay, 50 million new rows in our slowly changing dimension, our Type 2 slowly changing dimension every year. Remember, I only got 5 million customers only, but now we've got 50 million. Just after 1 year, we've got 50 million rows in our slowly changing dimension. After 5 years, we've got 250 million rows in our slowly changing dimension. Thinking about the reasons we do dimensional modelling, performance and simplicity, how's this going to perform when we've got a 250 million row dimension table joining to fact tables with millions of rows as well? Is it really going to perform? I say, no, that dog won't hunt. It's not going to work. Right. So the Kimball approved solution to this is that monster dimensions, so any dimension with millions of categories or millions of rows, must remain a Type 1 slightly changed dimension, which is not very helpful because there's probably a lot of attributes there that we want to track. We want to track changes to. We want to report historical facts against those historical attributes. So Kimball suggests we use what he calls mini dimensions. What we do is we take, in the star schema you see there, customer is down the bottom right. It is now a Type 1 slightly changed dimension. He suggests migrating all of those attributes that you are interested in tracking in Type 2 behaviours into mini dimensions. Okay, you group them according to logical groupings of attributes. Now I understand that concept is not easy to follow, so in the next few slides I'll try to explain it. So a customer might have some credit rating attributes, geographic attributes, behavioural attributes and demographic attributes as 4 rough groupings of attributes that we might be interested in. And there might be 8 or 10 different attributes in each of those groupings. Okay, so looking at just one of those mini dimension tables, and here's an example, the demographics dimension, what we do is we create a dimension table that has, as its non-key attributes, just has all of those demographic attributes in there. Okay, this table doesn't have any individual customer details at all. Note there's no customer number in there or customer natural key. All it is a table of demographic attributes. We've put in, for every different combination of demographic attributes, we put in a primary key, a new surrogate key, and then that surrogate key is used to attach to the fact when that fact is attached to a customer that has those demographic attributes at that time. So let's have a look at an example of the mini dimension. So say we received, just look at one customer. Customer might be me. In fact, this is my example. Male, single, aged under 25. Clearly, this is not a current situation. No dependents, low income. That was me at uni, right? And shortly after uni, right? Then we might receive another update to that customer, where that customer is now male, single. He's gotten older, 25 to 29, but nothing else has changed. Still no dependents, still low income. Okay, so what we do is we see that there is a new collection of demographic attributes that we've never seen before, so insert a new row into the dimension table. Right, then changes again. Male, married, 25 to 29. Actually, I was 29 when I got married. Still zero dependents, and my wife was employed. And now in a medium income group. I'd got a pay rise. Right. And then once again, this customer has changed again. Male, married, 30 to 39, gotten older. 1 to 2 dependents. I've got 2 kids. Still medium income group. So notice that there's no identifying customer attributes on this mini dimension. These rows are not specifically my rows. They could be used for, that first row could be used for any male uni student with no dependents and low income. So even though we might have 5 million customers, of which 500,000 of them might be male, single, under 25, no dependents, low income, we've now got one row in that mini dimension that covers all 500,000 of those customers. Right, so our mini dimension, as we see new combinations, we add new rows to the mini dimension. How big can the mini dimension get? Well, how many different combinations can you have? You've got 2 genders, say we had 2 marital statuses, 5 age groups, 4 dependents, 4 dependent groups, 3 income groups. That's 240 possible rows in that demographic dimension, right, which is a whole lot better than the 250 million that we expected to be in the customer dimension after 5 years of changes. All right, so mini dimensions, even though we're solving a type 2 slowly changed dimension problem, mini dimensions are still type 1 slowly changed dimensions. Right, so when I got older and I changed from the 20 to 25 age bracket to the 26 to 29 age bracket or whatever it was, I didn't end date and I did create a new row, but I didn't update the old row. Okay, so all I did is I found a new dimension. I found a new possible row to put in this dimension. So here's an example here. We've got this is a fact table, so we can see the date key. We've got 2 different days here, same customer. Okay, so this customer has had 2 sales, one on day 101, one on day 122. We're just using surrogate keys. We look up the date dimension to find out what days they were. Bought the same product, interestingly, from the same store, interestingly, right? But 2 different customer demographic keys. So we know that something about that customer has changed between the arrival of fact number 1 and the arrival of fact number 2. It's not recorded on the customer dimension, but we can see it in the fact table because it is attached to 2 different customer demographics rows. Right. Now, once again, in the new third edition of the book, Ralph has coined a new term for mini dimensions and called them type 4 slowly changed dimensions, which I think you'll agree is much more descriptive than mini dimensions. Right, type 4, we've done type 6, we've done type 4. On to type 5, slowly changed dimensions. So what we did with that customer dimension, we've just taken all of the good stuff out of it, really, all of those demographic, geographic, credit rating type attributes, and we've migrated them off to mini dimensions, right? Fantastic, but it's left our customer dimension a little bit bare. Okay, there's actually not much in there now that that tells us much about the customer. You've got name and address and phone number and email and stuff like that, right? But nothing interesting in an analytical sense. The very nature of monster dimensions, millions of customers with hundreds of descriptive attributes, even though we've migrated some of those descriptive attributes now, it makes them targets for analysis on their own. Okay, we don't need to just analyse our fact tables, right? So our sales and invoicing and deliveries and things like that. Customers are interesting on their own. You could ask many questions just about our customers. How many active customers do we currently have in the northern region? How many customers do we have in the 20 to 25 age group? Okay, these are things that would be interesting to decision makers in the organisation. So customer, far from being just a dimension, can become a fact in many of our queries. So what we do is we take those mini dimensions, take the keys of those mini dimensions, and we put them back into our type 1 slowly changing customer dimension. So customer, even though we migrated all those things out, we're going to add back in the key. So I've got our demographic key, our geographic key, credit rating, and behaviour key. So it's not type 2. It doesn't tell us what the demographics of the customer were a year ago or even a day ago. It's just the current demographic, the current geographic attributes of the customer. But we can answer questions like, how many customers do we have in the northern region? How many customers do we have in the 20 to 25 age group that are male with zero dependents, low income? So yes, we can't answer questions about last year on customers, but we can answer questions about now on customers, and those are the sorts of questions that might be interesting. Once again, Ralph has coined a new term for it, type 5 slowly changing dimensions. So these are two things that we do in combination when we encounter a monster dimension. Step 1, migrate those all of those type 2 attributes out into mini dimensions. Step 2, take those primary keys of the mini dimensions, put them back in the customer dimension as the current values. And we're not tracking history with those things, they're just the current values. The fact tracks the history. The sales fact tracks the history. Righto, leads us on to junk dimensions. Right, so now that we've explained the concept of a mini dimension where we take a set of attributes, we don't identify it to a customer, we've just taken a set of attributes and we say, oh, I haven't seen this set of attributes before, I'm going to create a new row in our dimension table. That concept is very relevant to junk dimensions. What we find, take our sales fact, right? Thinking of all the things about sales, we think about product, about time, about location or store, about customer, and we take all these attributes of a sale and we migrate those out to separate dimensions. We're often left with a few things. Last time I stood up here in front of you, we talked about degenerate dimensions, like the invoice numbers and things like that, things that are just specific to that sale. But that's not the only things. Degenerate dimensions are not the only things we're left with. Sometimes we're left with things that look like dimensional attributes. Think about these ones. This particular sale has a gift wrap flag. Yes or no that it was gift wrapped. Warranty replacement, voucher issued, voucher redeemed flag. These are things that are specific to the sale. It's not specific to the product. It's not specific to the location. not specific to time, not specific to customer. Okay, so we can't migrate it into any of our other dimensions. We're sort of left with these four things. So what do? Do we create, and they're not specific to each other either. Okay, they all behave independently of each other. So do we create 4 more dimensions against our fact table? Do we create a gift wrap dimension, a warranty replacement dimension with just 2 rows in them? Yes or no? So, and you could, certainly you could, but you would end up with, your SQL queries would have a lot of joins in them. They might be taking a SQL with 4 joins, expanding it out to like 8 joins. I've just put 4 attributes here. There could be more than that. Okay, expanding your SQL out, putting more joins in it, it's not going to make the SQL any faster. The technique that Kimball recommends on this is you take all these remaining low cardinality dimensions. They don't always have to be flags, yes and no, but they might have a small set of valid attributes. Say 5 or 6 or 10 attributes. You take all of those remaining low cardinality attributes and put them into what we call a junk dimension. Junk dimension, just like a mini dimension, every different combination or every different possible combination gets a new row in the junk dimension. And now we go back to our fact, our sales fact, and we just add 1 new foreign key to that instead of, in this case, 4 new foreign keys. Right, so we've created a sale junk dimension, which is unique combinations of gift wrap, warranty replacement, voucher issued, and voucher redeemed flags, and put them into the junk dimension. We take the key, the primary key of that dimension, sale junk key, we put that in our fact table. Now, when we're interested in any of those flags, we join our sale fact to our junk dimension. We have access to all 4 of them with a single join. But, okay, sounds great. Junk dimensions do have a restriction though. They're not conformed. Right? So think about one of those attributes. What do we have? Again, sorry, I'll go back. We had voucher issued flag, right? Voucher issued flag, yeah, you might issue a voucher on a sale, but you might also issue vouchers on promotions, on mail outs. Okay, we might have a mail out fact in our system. We might issue vouchers on that. We would have a voucher issued flag on that. We wouldn't have a gift wrap flag on our promotions table, right? Because we don't gift wrap our mail outs. Right? So what we can't do with junk dimensions is we can't share them amongst our facts. Well, usually we can't share them amongst our facts. Once we collect a bunch of junk from one fact, it's probably not the same bunch of junk that you're going to find in another fact, right? Which is usually not a problem. Usually you don't want to drill across on any of these junk attributes. But if you did want to drill across on a junk attribute, you can't anymore because you've collected it along with a bunch of other stuff. To have a conformed dimension, you need to be using, so if we've got customer, for instance, our promotions fact and our sales fact, right, if they both attach to the same customer dimension, means we can drill across. Right, we can look at the sales to that customer, we can look at the promotions that were sent to that customer, and we can compare behaviours. Right? We can't do that with junk dimensions. All right, so bear that in mind when you're creating a junk dimension. Not conformed limits your drill across capabilities. Okay, bridge tables. There's a bit of a, who's heard of bridge tables? Show of hands, yeah, lots of people, great. There is a bit of a trap with bridge tables. Bridge tables, many to many joins, yeah? Yeah, so what we often find, have a look at these two, the blue tables in the middle are our facts, the orange tables on the outside are our dimensions. Think of a doctor's surgery, we'd have a treatment fact, okay, that's the event when a doctor treats a patient. That treatment has one and one only patient. Okay, so patient's a good dimension for treatment. The treatment would also have a diagnosis. A treatment may have multiple diagnoses. So a single treatment might address multiple diagnoses. And so we have a many-to-many join between the diagnosis dimension and the treatment fact. Another one that's it's a bit closer to home, your insurance policy. Okay, insurance policy insures one item, right? But there may be multiple policy holders. You might, myself and my wife, will be joint policy holders on our home. Okay, so we've got a many-to-many relationship between policyholder and insurance policy. So this breaks our normal dimensional modelling standard of our dimensions and our facts having a one-to-many relationship. So how do we deal with it? If you're like me and you spent many years creating third normal form data models before you ever got into dimensional modelling, your first inclination, and this would be my first inclination, is to solve a many-to-many relationship with an associative entity. Okay, so we've got our treatment fact in blue there on the right. We've got our diagnosis dimension there on the left. And we say, well, if a treatment can have multiple diagnoses, we put an association entity in there. This treatment has this diagnosis and this diagnosis, 2 rows in the association entity. That's the natural inclination for a third normal form data modeler, certainly my natural inclination. But think about how this is going to work. Every single treatment in your fact table, remember our fact tables have millions and millions of rows in them, is going to have at least one diagnosis. And most of them are going to have probably exactly one. Right? So we're going to have millions of treatments, but we're also going to have millions of treatment diagnosis cross-reference records. Okay? How's performance going to be affected by having these 2 very large tables and having to join them? Okay? It's not going to be affected well. Okay? It's not going to be a positive outcome. In data warehousing, we acknowledge that we've got to deal with some very large tables. Our facts are always very large tables. But what we try to avoid is the situation where we're joining very large tables. Right, so think about another way to do it. Right? What if we took distinct groupings of diagnosis? Okay? There will be, most diagnoses will occur singly. You know, broken leg, flu. Okay, you've got one patient just has one diagnosis, or one treatment just has one diagnosis, and then and you're going to see that diagnosis repeated a number of times. Then there'll be ones where there are multiple diagnoses, but you might even see with those that they repeat. Okay, nothing's unique in this world. A person with one set of symptoms or set of diagnoses, you're probably going to see other people with that same set. And you can reuse, if you create a dimension called diagnosis group, which is 1 row per group of diagnoses that you have seen before in historical data, then you'll be able to reuse these rows. This diagnosis group table is going to have far fewer rows than the one that I showed you before that was just a cross-reference table. Right, so then our diagnosis group has 1 row per group of diagnoses that we've seen. We've still got our diagnosis table there on the bottom left, and now we have an association entity that resolves that many-to-many. So this group of diagnoses has these 1, 2 or 3 individual diagnoses in it. Right, let's have a look at an example. All right. Now, this is actually a real example. I know most of my examples were from me. This is from my mum. Okay, mum has osteoporosis. She tripped and fractured her tibia. When she was treated for that, there were multiple diagnoses by the doctor. Treated for osteoporosis and for the fractured tibia. Right, but when we have these many-to-many relationships, the first thing that pings in my mind, and maybe yours as well, is if you've got a many-to-many relationship, you're going to be exposed to potential doubling up when you write a SQL. Okay, a SQL that goes through these joins. You could end up with duplicates in your results. So in this example here, if I just joined my treatment fact through my diagnosis group and my cross-reference table to diagnosis, right, and I've got a fact, back on my fact, my treatment fact, I've got a billed amount on there, 250. I could get a duplication there. This looks like there were two rows. This treatment on 11th the 6th for osteoporosis, we charged $250. Same treatment on 11th the 6th. Different diagnosis, we charged $250. Is that a total of $500? Or did we just have one treatment for $250 with two diagnoses? Right, so we have to, when we're using bridge tables, we've got to watch out for cases where we get duplicates. So one of the ways to deal with this is putting a weighting factor on your bridge table. So this diagram here, I've taken off the fact. I've just got the diagnosis group on the right, diagnosis on the left, and the bridge table in the middle. Right, so we could say, for instance, of those two diagnoses, so the group of diagnoses that combined osteoporosis and fractured tibia, right, we could put perhaps weighting factors. We could put 40% against the osteoporosis and 60% against the fractured tibia. We could take these weighting factors and apply them to our measures. Right, so our $250 is no longer $250. It's been apportioned between the two diagnoses. Maybe that doesn't make any sense, but maybe it does in some situations. So weighting factors are one way that we can deal with it. Another way to deal with this many-to-many relationship is we could pick one as the primary. Okay, in this case, maybe the fractured tibia as the primary diagnosis. Osteoporosis is a secondary diagnosis, and when we perform our join through the group, through the bridge table to our diagnosis, we filter and we say, I only want the primary diagnosis. And then you only get one row out instead of two. You miss the fact that osteoporosis was was one of the diagnoses, but at least you don't get duplicates that way. So that's two ways to deal with it: weighting factors and a primary indicator in your bridge table. Righto, enough of bridges. Ragged hierarchies. This is something you see often in a customer dimension. Most of our dimensions have hierarchical attributes that roll up. Think of time, for instance. We've got days roll up into months, roll up into quarters, roll up into years. Nice and easy. Every level in these dimensions has a nice label that we can associate to it. Right? When we join our dimensions to our facts, we can say, show me the facts for the month of March, or the third quarter of 2013, or the year of 2014, right? So we refer to a particular level. What about when we've got, like this customer dimension, and it's got a ragged depth, okay? Our facts are attached to a particular customer, but that customer has its own hierarchy. The customer has a parent customer, and that customer might have a parent customer. It might keep on going up. We don't know how far it goes up. We can't even say, show me the facts for level 3 customers necessarily, because there might not even be a level 3 on one branch of the customer hierarchy, right? The sort of thing that we'd be interested in, looking at this diagram, we might say, show me all the facts show me all the sales for customer 2 and its subordinates. Right? We're not applying a nice hierarchical label. We're not saying, give me the facts for the level 2 customer, even though customer 2 does happen to be at level 2. Okay, we're just picking an individual customer out of it. So it's very, very difficult to, once you cannot label the levels in your hierarchy, like day, month, quarter, year, once they're all just, they're just customers. They have parents. I don't know how deep they are. Could go on forever. Once we can't label them, we run into difficulties. How do we even analyse them? Righto. So if you, like me, came from a third normal form background, what you do immediately is say, oh, that's easy. Each customer has a parent. It's a self-referencing relationship. How hard can that be? And it's not hard. It solves the problem in the model. Sure, you've got facts that join to a customer, and customers join to customers. So where's the difficulty? Okay, the difficulty comes in trying to write SQL for that. Right? So I've solved the problem as a model. I'll give it over to the programmers, let them sort it out. Okay? And then the user says, show me all the facts for customer 2 and its subordinates. Okay, so customer 2 might have 15 subordinates. Some of them might be 3 levels deep, some of them might be 4 levels deep, some of them might be 8 levels deep. Okay, how are you going to do all of those joins necessary to take customer 2 down to all of those different levels, and yet still join it to your fact? It is true that some modern business intelligence tools will do this for you. You just feed it your self-referencing dimension like that and say, sort it out. Okay, and the BI tool does sort it out. Not all of them will do this for you. Right. What we can do is we can create a table of pairs of customers. Have a look at this example and compare it to the diagram. We'll take customer 3, for example, on the bottom left. Customer 3, in its path back to the root customer, we pass through 3 different customers. Customer 3 itself, customer 2 and customer 1. We'll record all those pairs. So the child customer 3 has a parent of 3 itself. We record self relationships here. It also has a parent of 2, and it has a parent, not a direct parent, but an ancestor, if you like, of 1. We do this right through the hierarchy. For every single node in the hierarchy, we list all of the parents and ancestors of that node. All right, so how do we use it? So I've got 2 diagrams here. The top diagram is the physical model, how it looks. So I've got our sales fact. Every sale belongs to one and one only customer. Easy, okay, but we don't know where that customer is in the hierarchy. That customer has 2 relationships to the customer bridge table. Okay, it's a parent relationship and a child relationship. Just looking back quickly at our bridge table there, we've got 2 customer keys: child customer, parent customer, and that's those 2 relationships you see there between the customer and the customer bridge. We don't use it like that though. When we use it in our SQL, we use it like the bottom diagram. A sale joins to the bridge via the child relationship, and that's a many-to-many relationship. So the child customer 3, has many rows in the bridge, okay, many-to-many. The customer bridge has the relationship to customer via the parent. Each row in the bridge has just one parent, so that's a many-to-one. All right, so we've got a many-to-many join that we're going to use in our SQLs. How do we deal with that? So let's have a look at a sample SQL. Take it line by line. Select. Everyone got that one? Cool. From our sales fact. All right, so I've got our fact. Great. Now we're going to start joining it to stuff. Join to the customer bridge on the child customer key. Now remember that relationship between the fact and the customer bridge was many-to-many. So now every fact of just however many parents that customer has, including itself, right? I've just duplicated my sales fact by that many times, right? So now I've got, if I had 1 sale for customer 3, I've now got 3 rows in my result set. 3 with a parent of 3, 3 with a parent of 2, and 3 with a parent of 1. Okay, so then we joined a customer, right? Because we haven't got any details about the customer yet. We've still got to get customer details. So we joined a customer on the parent key. Right? Our parents are, for those 3 rows are 1, 2 and 3. Right? So we've still got this many-to-many problem, but we're just about to solve it with our where clause. Right? We're going to say, I actually only wanted customer ABC Proprietary Limited. Right? That might have been customer 1 at the root, it might have been customer 2 at level 2. And now my 3 rows, which all have different customers, right, collapse down to just 1 row. All right, cool. So I can now analyse my fact by any level in the customer hierarchy. All right, so it gives us, like I say at the bottom there, gives us all sales directly to ABC Proprietary Limited and all sales to subsidiaries of ABC Proprietary Limited. Right, but won't it return duplicate? For many-to-many joins, you're always going to get a potential for duplication. So, as I explained in the previous slide, if you filter it to a single customer, you're fine, because the many-to-many collapses down to 1 row as long as you filter to a single customer. But I don't want to always filter by a single customer. In fact, most of my queries I want to have a big group of customers. Yeah. So well, look, now you've got a problem. Okay, this is not simple dimensional modelling. It's advanced dimensional modelling, and you're going to have to come halfway to meet me here. So we've got, once we filter down to a single customer, we've solved our many-to-many relationship. If you look at that bottom diagram, our many-to-many relationship now turns to a many-to-one, right? But if we want to get multiple customers, consider if we said where customer name is in, and we listed the names of customer 2, customer 4 and customer 7, right? Those two customers at the bottom, customer 5 and 6, they're children of 4 and they're children of 2. So any fact that belongs to customer 5 and 6 is going to be duplicated in our result set. Right, so you've got a problem once you start selecting multiple customers. But if you can select customers from the same level in the hierarchy, you'll be fine. Right, so you can select, in some cases you can select multiple customers as long as you follow some rules. Okay? If you always select leaf customers or you always select customers at the same level, you're not going to get duplication. It's only duplications where you select 2 customers that are ancestors of each other. All right, so thinking about that, there's some attributes that we can add to the bridge to make our lives easier, right? To make it so that we can specify queries that will dance around this problem of duplication. So we could add attributes like the ones that you see here, levels from root, levels from parent. Okay, so if we're talking about the bridge row that has child 3, parent 2, levels from parent is 1. Yeah, how far between the two there are. We could flag root customer rows in the bridge or leaf customer rows in the bridge, and there will be a number of queries that we could apply to the SQL using these attributes that would keep us safe from duplication. In fact, in a good BI tool, but not good enough to solve this problem for us with the self-referencing relationship, we could build in logic to enforce the fact that you used at least one of these criteria whenever you use the customer bridge. Righto. So last time we met, we talked about 3 different types of facts. We talked about transactional facts or event-based facts. When something happens, we create a fact for it. We talked about periodic snapshot facts, things like bank accounts, where we take a snapshot of it every month, right? And each snapshot is a fact. We also talked about accumulating snapshot facts, things like an order. An order goes through a life cycle, we raise it, we approve it, we send it for provisioning, we send it for shipment, we close the order, and we create a row for that factor. We keep updating it every time it changes. That's the accumulating snapshot. These 3 types of facts all have something in common. They're all describing things that happen. Okay, but it doesn't allow us to analyse things that don't happen. Right. So, moving on to an example, we've got consider a vehicle rental. Okay, it's a nice easy one. Vehicles are rented from a depot on a particular date. You rent a particular vehicle and you, the customer, do the renting. Okay, pretty easy sort of event-based star schema. How could we tell from this star schema how many vehicles weren't hired for a particular day in depot? No, we can't. So what we need is another fact table. Something like this, for instance. If we had a fact table that listed vehicle availability rather than vehicle rental, okay, so at this depot, on this day, this vehicle was available. Right? We've got our other fact table that says what was rented on a particular day. We've got this fact table that says what was available on a particular day. We can combine the two. Sorry, that's the next slide. We can combine the two and answer questions about what vehicles weren't rented on a particular day. So looking at at what we call the factless fact, it's just an association of dimensions. So the fact table would have these 3 attributes on it: vehicle key, a date key, and a depot key. That just implies that this vehicle on this day was available at this depot. Right? Our fact table, we usually expect to see measures on there, you know, sales and quantities and things like that. But a factless fact or a coverage fact doesn't have any of these measures. It's just recording a relationship. Okay, this this was a valid relationship at this particular time. Righto, so there's an example. We've got our availability fact on the left, we've got our rentals fact on the right. We can see on day number 225 at depot number 9 there were 4 vehicles available, 1, 2, 3 and 4. We can also see on day 225 at depot 9 that 3 of those vehicles, 1, 2 and 4, were rented to 3 different customers, as it turns out. Okay? So we could write SQLs against these 2 facts, joining to their dimensions, and then we could combine the result to report the vehicle that wasn't rented, vehicle number 3. Okay? And then join that to the vehicle dimension and give details of that vehicle. Right. Okay, so factless facts, that's it. And in fact, that is all there is. Wrapping up what we've talked about, we've got hybrid slightly changed dimensions. We typically think about tables being type 1 or type 2. You'll find that's unrealistic. Some tables are exclusively type 1, that is true. Anything that we think of as type 2 is typically a hybrid type 2. There are usually type 1 attributes on that. And if we use our inbuilt type 2 behaviours that we get with our ETL tools that assume that the entire table is type 2, we might come unstuck there because they don't handle those complex behaviours of when those combo behaviours of when type 1 and type 2 changes. With our monster dimensions, we break out our type 2 attributes into mini dimensions, and that way we can leave our monster dimension as a type 1. Okay, it solves the problem of the monster dimension blowing out. Junk dimensions. Once we've taken out all our normal dimensions from our fact table, we're sometimes left with some low cardinality flags and the like. We can collect all those, even though they're unrelated, we can collect them all into a junk dimension. Bridge tables, they handle our many-to-many relationships between our facts and our dimensions. We create a bridge in the middle, but we think about it a bit first. We don't just go creating an associative entity. If that is going to generate another table that's even bigger than the fact table, we think about groupings. Okay, creating a grouping dimension. Ragged hierarchies. We explode out the hierarchy into pairs of child and ancestor pairs. Create a bridge table for it. Add some attributes to help avoid those many-to-many duplication problems, and coverage facts help us report on what didn't happen rather than what did happen. And that is all I have for you tonight. Nice and quick, right on an hour. I will throw it open to any questions. Got to be one. Yes.
Type 5 versus the factless fact.
Type 5 versus factless fact. This is where I hate the types. Now 5 was that one the mini dimension?
That you bring in the minis.
Mini dimension. Okay, so mini dimensions versus factless facts. Okay, so what's your question? Oh, mini dimensions back into the back into the type 2. Okay. Sorry, back into the customer dimension itself. So treating the customer dimension kind of as a fact, just with some outrigger dimensions on it. So versus a factless fact, it is, it's kind of storing relationships. It's analogous, I guess. What I'm trying to get at with coverage facts is the ability to tell what didn't happen, capturing the full superset of possibilities at a point in time. But yeah, certainly we can think of the customer monster dimension as a factless fact of sorts. That it is, we can query it like it was a fact, joined to those demographic and geographic dimensions as if they are dimensions of this fact. There are certainly no measures on there that we would like to aggregate. We're looking for particular combinations of low income earners in the we're not interested in low-income earners, we're interested in high-income earners in the Northern District. Yeah, there are certainly a lot of analogies there, but also the type 5, the monster dimension is a specific solution to a specific problem of monster dimensions.
Did you happen to touch on type 3 at all?
Type 3, I did last time. So
I just think you had.
yeah, if you send me an email and remind me, Murray now has the video from the last session up on YouTube. I can send out the link if you're interested in type 3. There, I covered an example on that last time.
It's also got chapters, so you don't have to sit through the other.
You don't have to. A lot of people want to, don't they, Murray?
It's not just log on to YouTube and see all this stuff, can you?
Once Murray gets it up, yeah, I acknowledge that Murray is doing this out of the goodness of his heart, and he does have a number of other commitments. We certainly cannot guarantee that the video of this session will be available tomorrow or even next week on YouTube. It will when it bubbles up to the front of Murray's list, then it will be on YouTube.
How do we find it?
I can send out once it's available. I can send out a link. I've got all your email addresses from Eventbrite when you respond to this. I'm happy to send it out when it becomes available. But having seen it all, maybe you're not interested in the video.
But the previous 2 sessions are they already available?
They are now. Quick show of hands, who would like me to use their email address that they gave to Eventbrite to get the links of the previous 2 videos? All right, enough of you. So I'm going to spam the rest of you with with those 2 links. My apologies in advance.
Just for your interest, so the ragged hierarchies actually resolve pretty easily with in SSAS.
Right.
So you can define the ragged hierarchy as a
Self-referencing relationship. Yeah. So
define it as a hierarchical connection.
Yep.
And it will solve all that sort of complexity for you.
Right. So SSAS is one of those lovely advanced analytical tools that do it all for you. So yeah.
There's actually, I don't know if anyone else has come across it. There's which I've never really used in the past, but there's a hierarchy data type as well in
Right.
Microsoft SQL Server.
Okay.
Which
Excellent.
gives you the benefit of using your dot parent, your dot child, going down, up and down the hierarchy.
Yeah. So that's certainly what we see is you often the way these things evolve is Ralph Kimball does both teaching and consultancy. What happens when he wrote his first book? None of these things were in the first book. He would go out to organisations that have implemented his philosophy, and they say, it doesn't work on this. I've got this dimension with millions of rows and hundreds of attributes, and look, I've made it a type 2, and now look at it. He goes, right, well, how are we going to solve this? Works out a solution, writes an article about it, gets all his cronies and various hangers-ons to refine the technique down, and he sticks it in his next book. So, and then it goes on from there that all of the product vendors, like Microsoft, build his teachings into the next version of their tools. So yeah, that life cycle certainly happens. And some of these other things that you heard about tonight, if they're not available in a handled automatically in an ETL tool or in an analytic tool, take a look at the next version. You might see some more stuff.
It's got some hierarchical self-referential query capability built into it now as well.
Right, so that's OBIE.
Yeah.
Yep. So
No, Oracle's just there.
right.
You can recursively, single reference to the table can join back on parent tree, you can go up or down.
Oh, you mean connect by statement?
Yeah.
Yeah.
It's not
So
terribly efficient, some of it.
yeah, you
It's
do.
there.
So those of you that are familiar with the connect by statement in Oracle, you do take a performance hit with the connect by every time you use that ragged tree. You cop the expense of the joins that it will take to resolve out the tree. Joins that are, if you look at the bridge table that I demonstrated here, are kind of pre-calculated for you. So I would expect, even though you could solve the problem with standard Oracle SQL. You might find you get better performance out of using a customer bridge.
And also it could be achieved with analytical functions as well, with lead and lag combined with that.
Lead and lag analytical functions to achieve
Ragged hierarchies.
ragged hierarchies. I'm not dismissing it, but I can't picture it in my head. Yes?
That customer, since we're talking about the customer bridge, that customer bridge table must have a pretty high cardinality, though.
Yeah, a few rows, yeah. So if you...
You commented earlier about joining high cardinality tables.
Right, so if you have... obviously it would be even worse if you combined it with a monster customer dimension. So yeah, if you had millions of customers and those customers were formed into a hierarchy of ragged depth, and the depth might be 8 or 10 levels deep, I could certainly see that every customer on average would have might have 7 or 8 ancestors. Yeah, does that sound about reasonable? So let's round up to 10.
Only 2, you've still got
Well,
double the
so
number.
say it's got 10 ancestors. So if we've got 5 million customers, 10 ancestors, we've got 50 million rows. Okay, that's not great, but it's not going to grow at the same rate as a type 2 slowly changing monster dimension that keeps on changing. Okay, so we're kind of capped by number of rows multiplied by average depth. Okay, 5 million rows by an average depth of 10, 50 million rows. Right, it's not going to get bigger than that. So, sure, 50 million rows is not ideal, but it is a very narrow table. It's just got those two key attributes and a couple of those other attributes, leaf flag, root flag, stuff like that. Not a terribly wide dimension, but difficult times call for difficult solutions. So, sometimes you tune it to a point beyond which you can't see any more opportunities to tune. So yes, you can get into that situation, but it's by no means as bad as a type 2 monster dimension. Anything else? No, looks like you all get off early, so thank you for coming along. So before you go, quick show of hands, if I do more of these, not on dimensional modelling anymore, but on ETL type things, anyone interested in getting an email? Once again, my apologies to those who didn't put their hand up. You're going to get a spam on when the next one comes out. So if you don't respond to that one, I will not spam you anymore. So at least it should just be restricted to the once. Thanks for coming along tonight. I appreciate it. And those of you that are interested, I'll see you again next time.